Hello everyone, this is Panghu from UMass Amherst. Today I'm going to present software-defined batteries. This work is done while I was interning at Microsoft along with my mentors and co-interns. The capability of phones have increased significantly in the last 15 years. For example, processing speed has increased by 1,000 times, and we have faster internet connectivity, larger screens, and more sensors. Unfortunately, the core technology that powers these devices, the batteries themselves, have not caught up. If we look at energy density by weight or energy density by volume, the battery have improved only by 2 times in the past 15 years. For example, the volumetric density of battery is 390 watt-hour per liter in 2000 and increased to only 720 watt-hours in 2014. So traditional batteries have no scale in density. However, the characteristic of batteries can be determined along several dimensions. For example, energy density by weight measures how much you can store in the battery per kilogram. Similarly, power density, affordability, and how cheap depends how cheap batteries are. And longevity means how long battery lasts. Flexibility means that the battery whether it's bendable or not. Different batteries perform differently along one of these dimensions, and not surprisingly, we can have a battery that excels in all these dimensions. For example, a startup from Israel have a new kind of battery that can be charged within only 5 minutes. However, its energy density is just 1/3 of the traditional batteries. Similarly, a startup from Taiwan have a bendable battery, but the efficiency is only 75% when compared with the traditional batteries. So we find that every battery has an advantage and a disadvantage. What can we do? Do we wait for the perfect battery that improves upon all metrics that has not been developed for the past so many years? Instead of playing this waiting game, we take a different approach. Our insight is that by effectively combining batteries with different chemistries, we can hide their drawbacks and exploiting their benefits to mimic a perfect battery. So how do we connect batteries of different chemistries? Can we simply connect them in parallel? By doing this, the batteries have to have identical chemistry with similar discharging curves. Otherwise, you either overcharge one of the battery or undercharge another. Similarly, is it possible for us to simply connect them in series? The problem is that the battery with larger capacity will still have a remaining charge inside the battery when the battery has a smaller capacity shut down first. This causes a great waste of energy. To conclude, there's no easy way to to connect different batteries together. There's a need for fine-grained power control flows in and out of each battery. In addition to that, power also determines characteristics of batteries such as efficiency and longevity. When discharging a battery, you can't get 100% efficient due to their internal resistance. The loss is proportional to the square of power you draw from the battery. Similarly, charging power also determines the rate of the battery wear out. From the figure on the top right, we can see that anode degradation and due to the structural cracks, and this results in loss of capacity. And this speed can be faster if we use a higher charging power because of the nonlinear aspects of the anode degradation. For example, if we charge a lithium-ion battery with 1 ampere, the remaining capacity will be 88% after the 600 cycles. However, if we discharge it with 0.5 ampere, the remaining capacity could be 88% instead of 77. Inspired by this, we introduce our solution to the two challenges we have mentioned. Firstly, we need to combine batteries of different chemistries. Secondly, we need to control the power flows in and out of each battery. Our solution is software-defined batteries. In software-defined batteries, the operating system can dynamically determine the charging and discharging power from each battery according to the capacity, aging, power density, and the current and plus future workload of the operating system. At a high level, there are three components in the SDB system. First is the battery with different chemistries. And second is SDB hardware that has the ability to control at a fine-grained amount of power going in and out each of the battery, which the value can be set to the microcontroller. And the third one is the SDB software that determines the power value by using various algorithms. A policy engine determines what power value to set based on customizable algorithm, and the driver convey these values to the hardware that enforces them. Although we can implement SDB software in the microcontroller, or even with the entire hardware, we decide to put the logic and the intelligence to the software side. This allows the SDB to use information from the rest of the OS, and we can leverage the user behavior, and more additionally, we can make the hardware cheaper and the system future-proof. SDB span innovation across different aspects, including chemistry, hardware, and OS design. We now describe each of the innovations one by one. For the SDB battery, we have sampled several new kinds of battery including faster charging, high energy density, from several manufacturers and startups with interesting characteristics. SDB can work with various kinds of energy sources, including supercaps. Let me proceed to the SDB hardware design. The goal for the SDB hardware is twofold. Firstly, we want to achieve accurate and efficient power flow control both in and out of the battery. In addition to that, we also want to have a low-cost and a small form factor hardware that has minimal silicon overhead. To be more specific, we want fine-grained load sharing across batteries when discharging, and flexible charging across different batteries, and even the ability to charge one battery from another. Fine-grained load sharing can be achieved by switching two batteries at a high frequency using an electronic switch. And by configuring the time the switch spend on each battery, we can determine the power you draw from each battery. A naive way to implement this scheme is to have an electron switch, microcontroller, and a capacitor to smooth out the fluctuations. However, this method has a disadvantage that it requires additional hardware. And to make matters worse, it will reduce the system efficiency and increase the cost. Can we leverage the existing hardware to solve this problem? Today, every mobile device uses a switch mode regulator that converts the exterior voltage into the desired voltage. So we take advantage of the existing hardware, and by modifying the switch regulator, we can add several gates before the regulator, and we can switch between the batteries and join configurable amount of power from each battery. To do this, we only need a few extra gates. The cost is much lower. Now, we move to the SDB charging hardware design. Adjusting the charging power can be done using a similar technique as we have described in the SDB discharging section. However, we need an energy-efficient scheme to charge one battery from another. Considering that batteries can have different voltages, so we need to have n-square regulator to achieve all the n-square combination of charging and discharging pairs. This system just does not scale as the number of batteries increases. Our solution is that we can modify the regulator and making it work reversibly and in an efficient manner. By doing this, we reduce the number of regulator from n squared to simply n. We introduce microbenchmark experiments to determine the efficiency of the SDB hardware. We first present the efficiency result. For the discharging hardware, the loss because of the hardware components is between 1 and 2%. For the charging hardware, the efficiency is more than 93%, and the loss is due to the modification of the reversible regulators. However, we find that the reverse regulator is only 2% less efficient when compared with the traditional regulators. We now present the accuracy results. For various charging and discharging settings, we find that error, which is defined as the deviation from the desired power ratio. No matter when we set the discharging proportion to 1% or 99%, the charging current set to 0.2 ampere or 2 ampere, the error is always less than 1%. Although our current SDB hardware implementation includes 3 PCB boards, but we find that it's completely possible to integrate everything into an existing power management IC. The cost of the ideal silicon is in the order of tens of cents. Finally, we do not increase the weight and the volume of the hardware because we are not adding additional chips. Okay, I think I have bothered you guys enough with these hardware details, and I will describe the SDB software. That is probably more to your interest. Modern OS using ACPI to communicate with the battery device. However, they do not allow the driver does not allow the driver to configure these batteries dynamically. To do this, we define a simple set of APIs that allow the driver to configure battery via the microcontroller. So firstly, we have the discharging API that allows the driver to set the power ratio drawn from each of the batteries. And similarly, the charging API that can be used to determine the power you send to each of the batteries. We also allow the driver to charge one battery from another with a given power, charging power and a given time duration. Finally, we have an API to query the status of these batteries. We also have the policy engine that has the logic to determine these ratios using user, workload, and battery knowledge. We now describe the algorithm, API, and system software that's needed for the SDB system. For simplicity, we only describe the discharging side of the talk, and I encourage you to read the paper or come into our poster session for more details about the charging solution. The charging problem at high level can be defined as the following. So the system needs power I. How much should we draw from each battery? Naturally, we have two algorithms. The first algorithm is that we can minimize the losses, and the second algorithm is that we want to balance well. For the first algorithm, we define the loss as I1 square R1 plus I2 square R2, where R1 and R2 are the internal resistance of these batteries. By minimizing the losses, we want to achieve the goal that the device can last longer through the day. And similarly, for the balanced well algorithm, we define a well level of the parameter of the battery. This indicates the remaining capacity in the battery. For example, if the battery after a certain cycle count, the battery has only 60% of the amount of available capacity when compared with a new battery, then W is equal to 0.6. By using this algorithm, we find that we can draw proportional power from the battery with regard to their wear-out level. The goal of this algorithm is to make the battery last longer. These two algorithms seem to be similar, but I will still that they do have contradictions. Consider a use case that not all the users always cycle the battery from 100% to 0. Usually, They charge the battery when the remaining charge is low, for example, between 5% to 20%, and they will start to charge. If we're always using the minimizing loss algorithm, then the battery with lower internal resistance will be discharged and charged for more times. So this will result in a worse wear level for this battery. This goes contradictory with the balanced wear algorithm. Given that we have this contradiction, how can we solve this problem? So in the SDB API, there's a need to convey the various requirements of the SDB policy engine to match the need of the users. Our solution is that we can add a parameter to meet the user's needs. With this parameter, user can determine between minimizing loss, balanced aging, or even a hybrid one. However, most user needs are dynamic and change over the course of a day. Therefore, a system that chooses to be optimal at every instant may not be globally optimal. We must rely on the SDB software to account for future workload when they are predictable. Conserving an energy-efficient battery for non-high current workload in the future is a good idea. Recall that loss is proportional to the square of current, and this creates opportunity in the future. For example, if we know that the user is going to turn on the GPS at 6 p.m. every day, then it can be more efficient to conserve the charge in the more energy-efficient battery to account for that load. We abstract the workload prediction model from the SDB software system. We modify the OS power manager to estimate the current and future workload. And based on that, we set the parameter which ultimately determines the ratios. For example, if we know that there's no high power workload in the future, then it makes sense to minimize instantaneous instantaneous losses. And otherwise, we need to conserve the energy for the future. Our charging algorithm is also likewise challenging and interesting. I encourage you to read the paper to understand our design for charging the batteries. In summarizing SDB software, we note that we only scratch the surface of the algorithm that can help to improve the efficiency of batteries. Some of the advantage of our system includes that if we want to add new batteries for the next version of a device, or if we want to have some new algorithm, or if we want to exploit new user patterns, we actually don't need to make any change to the hardware. Everything can be done in software easily. This approach hastens innovation, reduces costs by keeping the hardware simple, and also helps the system easily interface with the rest of the OS that has the knowledge of user and application workload. Before I describe some SDB case studies, I'd like to describe the SDB modeling platform that we have built. It has a battery modeler that is based on real battery data for more than 11 different batteries. It also includes an emulator hardware that was previously described. We also verify the accuracy of the simulation with industrial level devices. Where various application traits have been included in the platform, like gaming, email, notification, video watching, listen to music, CPU, GPU benchmarking, and other workload for production smartwatch, phones, and tablet PC. This platform can enable fast evaluating the performance of batteries and an algorithm without charging and discharging a battery for hours. It also makes the experimental result repeatable and does not explode the battery if you want to experiment with the crazy algorithms. So let's take the flexible battery for wearables as the first case study. Wearables today are severely battery constrained because they are worn on the body. They often have strict weight and size constraint. However, a possible solution is that we can use flexible batteries. That without increasing the bulk, we can embed the flexible battery in the wristband. However, flexible batteries are unfortunately less efficient when compared with traditional lithium-ion batteries. with SDB, we can integrate lithium-ion batteries with flexible batteries. And a simple policy could be to minimizing resistance loss. And however, we compare this to a SDB setting that knows the user workload and show how such a knowledge can help to improve the battery life. We begin this experiment by extracting the energy usage trace of a smartwatch equipped with the GPS. Notice that the y-axis, which is energy needed used by the workload, is in log scale. We can find that there is a significant spike at 9 a.m. This happened when the user enabled GPS and went for a run while wearing the smartwatch. For the rest of the time of the day, the smartwatch remains in standby mode and deliver the notification in a steady state. Now, let's see the amount of energy wasted by the two batteries if we use the algorithm that minimizing instantaneous loss. We find that there's a significant change before and after the GPS workload. This is because that if we want to minimize the instantaneous loss, we essentially draw more charge from the battery that is more efficient. However, during the GPS workload, the high efficient battery depletes, and for the rest of the day, the smartwatch has to rely on the less efficient flexible battery. Now, let's say a different algorithm. If we conserve energy for the future workload, we can find that the amount of energy wasted at the beginning of the day is slightly higher because we tend to draw power from the less efficient battery. However, during and after the GPS workload, we are more efficient because we still have remaining charge in the more efficient battery. Overall, the system can have at least 7% longer battery life when compared with the minimizing instantaneous workload. SDB also helps improve the efficiency of external battery packs, such as the base of 2-in-1 laptops, battery case of phones, and also portable battery chargers. Today, external batteries charge internal batteries, and this wastes a lot of energy due to the inefficiency of the battery. However, SDB can use to reduce such loss by drawing charge from both internal and external batteries. If the battery is plugged in for only for long duration, then there's no need to cross charge. And if the battery is plugged in for only a short duration, then with SDB policy, we will charge the internal one with external ones. We demonstrate the opportunity that exists if we are able to correctly predict how user will use the external batteries, especially in the case of a cable base of 2-in-1 laptops. We compare with two extreme use cases here. The first one is that the user always plug in the external battery, and the second case is that the user plug in the external battery only when the remaining charge is low. We see that if we are able to predict the user behavior, this will result, we will increase the battery life by as much as 23%, depending on the user behavior. To summarize, for the first time, battery has become a resource that can be managed with the operating system with software-defined batteries. The power coming in and out from the battery can be adapted based on the workload. This enables many new application scenarios in increasing the capacity of the battery and reduce the charging time reduce charging time. In the future, we plan to integrate SDB with the calendars and smart assistants such as Cortana. In addition to that, there are many interesting applications such as that we can apply the software-defined battery to electrical vehicles. So by determining the information of the road, such as incline, temperature, and traffic, we can extend the range of the electrical vehicle. Other potential application includes increased drone flight time based on the wind condition and the flight passes. With that, I would like to end my talk, and I'm happy to take questions. Thank you.
Mohammed Katib, HGST Research. So just one clarification question before I ask the main question. Why would you need another battery with a different chemistry? What is exactly the scenario that you are targeting here? Is it shaving peaks, or what's exactly?
So I think you're asking a reason why do we need to have batteries with different chemistries, right?
Right.
So basically the case is that you can see the increase of battery capacity, battery density is very slow. So we need to have, and there's no battery that excel in all these dimensions. So we wish that, okay, so.
I get that. I mean, okay, I get the longevity, cycles, everything, I get that. Okay. What my question is, in your case studies, yeah, when do you plug the second battery, and what is exactly its contribution here? When you are predicting future workload, is what you are targeting because you are expecting a high current surge, you want to shave that off by plugging a battery that gives you high current, or what's exactly the scenario, the electrical scenario?
Can you repeat your question? I'm a little bit confused.
Okay, maybe we'll take it offline. Okay. Just maybe a comment here. You can even plug battery of two batteries, same chemistry with very different characteristics. Maybe you ought to take a look at LiPo batteries, lithium polymer or other kind of batteries. You can have the same chemistry and gives you all kind of, basically the graph that you were showing. Thank you.
Thanks.
Markus Hähnel, TU Dresden. I have a question regarding security. When you move the functionality that's currently in the microcontroller that controls the batteries to a software-defined battery, how do you ensure that limits on the battery chemistry like charging current and voltage, maximum voltage are enforced, and that there's no compromise to physical security of the battery?
So you are worried about the security of the SDB software system. I acknowledge that giving the flexible control of the battery increase the availability of the SDB of the vulnerability of the batteries. However, the batteries themselves have the hardware protecting circuit. For example, if you want to overcharge it with excessive current, the fuse will blow, and you can essentially can't do that. So we have the hardware limitations that you can't be exceeded with the software.
Okay.
Is that clear?
Thank you. Yes, sir.
Hi, Jason Flynn. So my interpretation of one of your goals, which is balancing the wear, is that you're trying to make the batteries wear equally. But my real goal is that I want my batteries not to wear. I want to reduce the wear. And so my question is, can you help me achieve that? Because it appears that the charge-discharge behavior is going to have a pretty negative effect on battery lifetime.
Let me navigate to the slide. So essentially what you ask is that why do we have to have the algorithm that need to balance the wear, right? Or a different?
I'm asking about the goal of balancing the wear. It seems like your goal should be to reduce wear or to minimize the extra cost in wear.
Actually, the reason for us to balance the wear is that I think it's pretty close to what you are saying, that we want to minimize the wear. But sometimes but we find that in most scenarios, and balancing the wear is the best case to minimize the wear. And here we're using a simple proportional wear algorithm, and I believe that with more case study you can find an even sophisticated algorithm that determines the power you draw from each battery that can have a better wear level policy. And we use the balanced wear here just as an example. So we offer the SDB software platform, and we think that this can enable innovation from multiple aspects, including new strategy for wear out these batteries. Yeah. And
okay, thanks.